I'm Miles Budemer, Motion Control Editor with Design World Magazine, and welcome to our Motion Control Selector video series. In this episode, we look at some selection tips for bearings. When specifying bearings, you have to consider and evaluate a host of application-related factors in order to get the best design. Here's an overview of some of the more important factors to consider when selecting a rolling bearing. The first consideration is the available space or design envelope. In many cases, one of the principal dimensions of a bearing, the bore diameter, is predetermined by a machine's power design and the resulting required shaft diameter. In general, small diameter shafts typically incorporate all types of ball bearings, while roller bearing types usually will be specified for applications featuring large diameter shafts. When radial space is limited, bearings with a small cross-section, especially those with a low cross-sectional height, can be a good fit. When axial space is limited, designers will want to specify bearings that can handle radial, axial, or combined loads. Next, consider the applied loads. Bearings must always be subjected to at least a given minimum load to provide for proper rolling element rotation and enhanced lubricant film formation in rolling contact areas. The magnitude of the load is one of the factors that usually will determine the type and size of the bearing for any given application. Generally, roller bearings can support heavier loads than similarly sized ball bearings, and bearings incorporating a full complement of rolling elements can accommodate heavier loads than corresponding caged bearings. Ball bearings are mostly used where loads will be relatively light or moderate. For heavy loads and where shaft diameters are large, roller bearings are typically recommended. The direction of the load also will come into play in selecting bearing type and size. Some bearings can only support pure radial loads, while all other radial bearings can accommodate some axial as well as radial loads. Other types have been engineered to handle purely axial light or moderate loads. The rotational speed is also a critical factor. The speed limits for a bearing are governed by the specific design and material of the bearing components and the permissible operating temperature for the type of lubrication system being used. Bearing type and size, internal design, precision, loads, lubrication regimens, and cooling conditions, as well as cage design, accuracy, and internal clearance, will combine to establish the speed capability of a bearing. Basic thermal reference speeds will provide designated values to determine the permissible operating speed of a bearing at some defined operating temperature, when subjected to specific loads and lubrication conditions. Bearings can potentially operate at speeds above the reference speed when bearing friction is reduced or when heat is removed. Also, the stiffness of a bearing is similar to the stiffness of a spring and is characterized by the magnitude of the elastic deformation or resilience in the bearing under load. In general, this deformation is small and can be neglected. In some cases, however, stiffness becomes a critical factor. In general, the contact conditions between rolling elements and raceways in roller bearings provide a higher degree of stiffness compared with similarly sized ball bearings. A bearing preload enhances system stiffness and provides other advantages by reducing running noise, promoting the accuracy of shaft guidance, compensating for wear, and settling processes in operation, helping to contribute to longer service life. A preload basically imposes a negative operational clearance in a bearing arrangement to achieve these benefits. Depending on bearing type, the preload may be either radial or axial. When bearings operate without any load or under light loads and at high speeds, preload should be imposed to provide a minimum load on the bearing to prevent bearing damage that may result from sliding movements of rolling elements. Preload can be accomplished in several ways, including the use of springs, washers, friction torque, or adjustment procedures, among others. Lastly, consider the bearing arrangements. Commonly specified arrangements include locating and non-locating, adjusted, or floating versions. You can choose from a wide range of locating, non-locating bearing combinations to achieve specific performance objectives consistent with application demands.